Welcome to Notes Number 1, Intro to Stoichiometry. Stoichiometry is kind of fun. It's the heart of chemistry. We have done so many things this year to build up to this. This is like finally playing the game. You've learned all your skills, and now you're going to put it together. So stoichiometry rules, according to Miss A: correctly write and balance the chemical equation. And number 2, convert to grams. So if you're not in grams, you got to get to grams. Then third, you got to convert to moles. So if you're already given moles, you don't have to have anything to do with grams. But if you're in some form of kilograms or milligrams, you got to get it to grams, and then from grams to moles. And then number 4, you're going to do something we haven't done before. You're going to use the mole ratio, which is from the coefficients in the balanced chemical equation. And those, it's just really the ratio of the coefficients. And then we use what we're given to try to find what we're trying to find. And number 5, convert from moles of what you're trying to find to grams, if that's what the question's asking. Sometimes you can stop at moles, which saves you a lot of work. So in general, you're going to go from grams to moles, so grams of the given to moles of the given by dividing by the mass of the thing you're given, and then moles to the thing you're trying to find by using the mole ratio, and the moles of the thing you're trying to find is on top, and the moles of the things that you're trying to get rid of is on the bottom, and then you'll convert those moles to grams if that's what the question's asking. It looks a little bit like this. So grams you're given over 1. These are the best railroad tracks I could come up with in the moment. And then you'll convert from moles to grams to moles, and the mass from the periodic table down here. And this is the mole ratio from the balanced chemical equation. They should always be whole numbers. And then you'll convert from moles to grams of the thing you're trying to find. Again, that is from the periodic table. So for example, for the following, balance the equation, solve using proper units, conversion factors, element compound symbols, and sig figs. So question number 1, use the following unbalanced equation to A, balance, you're going to balance the equation above, and then you're going to find out how many grams of NaNO3 can be made from 67 grams of sodium. So we have our start, and we're trying to find NaNO3. And this is a separate question, but it is still related to this equation. So what mass in grams of hydrogen gas? So then in letter B, we'll try to find hydrogen gas produced from 67 grams of sodium. So they made it a little bit easier for us that we have 67 grams to start with in each of those. So we'll have some repetition in numbers that we can copy. So the first thing we have to do is balance the equation. And we always need to balance the equation. And we'll start here. We have 1 sodium and 1 sodium. Those are balanced. 1 H, 2 H's, not so balanced. And I have 1 NO3 unit and 1 NO3 unit. So that's balanced, but my H's aren't. I think I need to put a 2 in front of there. So now I have 2 H's and 2 H's, but now I have 2 NO3's. So I'm going to need to put a 2 in front of NaNO3, and that gives me 2 NA's, so my final piece is to put a 2 in front of there. So now we're going to solve this problem. So we're going to start with 67 grams of sodium, so Na. We'll make our railroad tracks, and if you remember from up here, we will have the given part, and then we'll need 1, 2, 3 parts of our railroad track. So here we go. And that's the starting part, and then we'll need that part, and we'll need the mole ratio, which is that part, and then we'll need the final part, and then we'll hit equals. So in this next one, we will always have 1 mole right there, and that'll be 1 mole of sodium. I'm going to shove in there. And then in this last part, the mole is going to be on the bottom, and the grams are going to be on the top. And this is moles of the thing we're trying to find, which was NaNO3. My finger's a little chubby. It's hard to get it all in here. NaNO3, that looks a little ugly. And down here I'll have grams, and that'll be grams of Na. That's why I've always written my elements or compounds in there so I don't lose track. And then here's the mole ratio. So we're going to have moles of the thing we're trying to find over moles of the thing that we already have. So that's going to be moles of Na, and the top is going to be NaNO3. This is really ugly, isn't it? Holy crud, I'm taking up a lot of space. So let's go in and fill in some of these numbers. So for right here, we need the mass of sodium. So I go to the periodic table, and it is 22.99. And then I'm going to skip and go clear to the NaNO3, and I'm going to the periodic table, add up 1 Na, 1 N, and 3 O's. That one's 22.99, 14.01, and that would be 16 times 3, and that is 84.99 grams. And then we have our last part, which is the mole ratio. So the moles of the things we're trying to find on top, and the moles of the thing that we are trying to get rid of on the bottom, and that comes from the balanced equation. So we'll have 2 for Na, and then the NaNO3 will also have 2. So it's really a 1-to-1 ratio, but I write in the actual numbers. In my head, I see it as 1-to-1, but on my paper, I write it as 2/2. And then we do the math. And let me write out what the math in my calculator would be. It's going to be 67 grams divided by 22.99. I'm a little bit lazy here with my calculations. Times 2 divided by 2. I don't use parentheses. Then times 84.99. And bada bing, bada boom. We have to consider sig figs. So this, we started with 2 sig figs, so we can only end with 2 sig figs. The number in my calculator says 247.7, but that's going to round to 250 grams of NaNO3. And it's 250 because there's the first sig fig, there's the second sig fig. That one doesn't count, but it's holding a place. And then we put our geometric shape around here, and we go, woo-hoo! I'm going to do some erasing, and then we will erasemate, please. Then we will start this next one. And the great thing is that we already have some of that information that we can reuse. It's a little bit like recycling. I'm not sure if it's good for the environment, though. Let's do black. Why not, people? So 67 grams of sodium. And I'm going to have the same ding-dong-dang train tracks. Do, 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 equal sign. And here I'm going to have 1 mole. And again, that was going to be 1 mole of sodium. And there's going to be grams of sodium. And over here is going to be 1 mole of the thing I'm trying to find. Let's take a look. I'm trying to find hydrogen gas, which is H2. If my fingers weren't so wide, I could probably squeeze this in a little better. And that one's going to be grams of H2. And I know that one's 2.016 because it's 1.008 on the periodic table times 2. The sodium was already written there, so I'm just going to rewrite that down there. So 2.99. Oh, this is looking ugly. It's kind of driving me crazy. And then we do the mole ratio. I love the mole ratio. That's always whole numbers. Who doesn't love a whole number? So if you had 2 in that one, because you started with sodium, it's got to be 2 there also. So I'm going to do 2. I'm going to get lazy and do 2 NAs. And on the top, I've got to do the thing I'm trying to find, H2. And in front of that H2 is a 1 that just isn't written. So then there's 1 H2. In my calculator, I'll do 67 divided by 22.99. I'm going to ignore the times 1, but I'll do the divided by 2 because it's on the bottom. Then I'll do times 2.016. And if you do some mental math, you might be able to do this. Maybe, maybe not. And so in your calculator, I'm not sure what your raw answer is, but you have to round it to 2 sig figs, and it's 2.9 grams of hydrogen gas. Then for letter C, It says if there is 67 grams of sodium, how many grams of HNO3 are needed to react with it? So again, if we have 67 grams of sodium, so we're starting with that one, how many grams of HNO3? So we're going to do stoichiometry from Na to HNO3, and if you haven't noticed, once we have one item, we can find the mass of everything else with a line of stoichiometry. So there's a line of stoichiometry, there's a line of stoichiometry, and we can do one more line of stoichiometry in which we go from sodium to there. It doesn't matter which side of the arrow it's on. So for letter C, we start with 67 grams of sodium. We change from grams to moles. Those grams are from the periodic table for sodium. Then we do the mole ratio, and there's 2 moles of Na. See, there's 2 moles of Na. That's where I got that from. And then 2 moles of HNO3. That's just that number in front, the coefficient. And then we change those moles of HNO3 into grams of HNO3. So we add 1 H, 1 N, and 3 O's, so 63.02. And the calculator, 67 divided by 22.99 times 2 divided by 2 times 63.02. And we have 2 sig figs, so it rounds to 180. That 0 is just holding no place. It doesn't have significance because there's no dot there. And this question then asks for 3 lines of stoichiometry. There's 1 line, 2 lines, 3 lines, and in essence we took the mass of that one that was given and we found that item, and that item. And it doesn't matter where the item is, on the left or the right of the arrow, we can find them all given one item. Looks like I didn't number very well for this. I went straight to number 3. Apparently there's something wrong with number 2, and I just ignored it. So question number 3 says water is produced. So water is produced when hydrogen gas is reacted with oxygen gas. So since you're not given the equation, you have to balance this out. And I think this question might be one of the last questions on your web assignment, so refer back to here to help you. So write and balance the reaction above. So when hydrogen gas, that means H2, is reacted with oxygen gas, that means O2, it produces water. Produces means arrow, and then we do water. So hydrogen gas is H2 because it's diatomic, oxygen's O2 because it's diatomic, and then we balance it. There were 2 H's and 2 H's and 2 O's and 1 O, so we had to put a 2 in front of here to get it. 2 O's, 2 times 2 was 4 hydrogens, so I put a 2 there. Question B says, how many grams of hydrogen gas are needed to produce 5.50 grams of water? So we write 5.50 grams of water. And in fact, I like to go back to my equation and write down what I have and where it's located. So I have 5.50 grams of that. And again, I have to go back to the question because I have short-term memory issues. How many grams of hydrogen gas? So I'm going to do a line of stoichiometry from water to the hydrogen gas. And that looks like, so 5.50 grams of water. Change it from grams to moles. I got 2 hydrogens, 1.008 times 2, plus oxygen, which was 16. That added up to that. It was from the periodic table. This part is the mole ratio. There's 2 moles of water. I got it from there. You have to balance the equation. And we're trying to go to hydrogen, so you find the number in front of that, which is 2. And then you change the moles of hydrogen into grams. And by adding up the molar mass of hydrogen, you do 5.50 divided by 18 times 2 divided by 2 times 2.016, and you get 0.615 grams of hydrogen gas. 3 sig figs ending, because I started with 3 sig figs. And just because I can, I'm going to slash. I'm the mole and gram slasher, unit slasher, grams. I love to check and make sure I have everything in order. Question B, question C, asks how many grams of oxygen gas are needed to produce 5.50 grams of water. So we're trying to find how many grams of oxygen gas from that. So we're starting with the same number, and instead of going to hydrogen gas, we're going to oxygen gas. So we have 5.50 grams of water. We change from grams to moles, and then we do the mole ratio here, and there's 2 waters there, just like we had 2 there, and then the thing on the top is the one we're trying to find. Go up there, and there's a 1 in front of O2, a mysterious, magical, invisible one, and so we put a 1 there. And then we change those moles of oxygens into grams, and each oxygen is 16 times 2 is 32. We do the math 5.50 divided by 18 divided by 2 times 32. Notice I'm ignoring the ones. Start with 3 sig figs, end with 3 sig figs, 4.88 grams of oxygen. And looks like we answered those questions. Question number 4 is ammonium hydroxide is reacted with copper 2 nitrate in a double replacement reaction. So here we go back and we have to write these out. So ammonium hydroxide is reacted with copper 2 nitrate, and a double replacement is the front parts switch. So Cu then becomes attached to the OH, but that was a 2+, so you need 2 of those. And then the ammonium part connects to the nitrate. The ammonium is a 1+, the nitrate is a 1-, so you just need 1 of each. There are pretend invisible parentheses in there that each have 1s on the outside. Again, they're pretend and invisible, just like the invisibility cloak. And anyway, it said we have, the next problem is what is the mass in grams of copper 2 nitrate, so we're trying to find that one, to react with 72 grams of ammonium hydroxide. So we're doing a line of stoichiometry from there to there. So 72 grams of ammonium hydroxide, we go grams to moles, and then we do the mole ratio. There's 2 of those for one of those. Again, I got from the balanced equation, and then 1 mole of copper nitrate to the molar mass of copper nitrate. 72 divided by 35.05 divided by 2 times that will give us that. And we have 3 sig figs because we started with 3 sig figs. And now we're going to move on down to the next question. So given 72 grams of ammonium hydroxide, how many grams of ammonium nitrate can be produced? Same song, different key. 72 grams of ammonium hydroxide. Thank goodness we did it up here. We'll do grams to moles. 2 is still the same, but in front of ammonium nitrate, there's a 2 in the balanced equation. Don't believe me? Let's take a look-a-loo. And there it is. There's the 2. And then we change the moles of ammonium nitrate into grams by adding all that up from the periodic table. 72 divided by 35.05. Ignore those. Times 80.05. And it looks like we get 164 grams of ammonium nitrate in a lovely geometric shape. So hopefully you understood what we were doing there with stoichiometry. I find stoichiometry to be fun. This is awesome on our COVID-19 days at home that we can learn from Miss A, and you don't have to look at me. It's amazing. So again, you do grams to moles of the thing you're given, and then you do the mole ratio, which is from the coefficients from the balanced equation, and then you change those moles into grams. If I were to ask you just moles of ammonium nitrate, you would X that out and you would just hit equals. If I were to give you moles of ammonium hydroxide, this would be your starting point, and then you would just use that and that. But I should not have that in your WebAssign. So your assignment after you do this will be on WebAssign. Feel free to email me if you have any questions. Good luck to you.